Hello everyone, welcome to the week 7 of the pattern recognition and application course problem solving session. So as you know, I am Tanuka from IISc. I am a PhD student over there in the electrical engineering department. So in the last week we were talking about dimensionality reduction and we solved problems on one particular way of dimensionality reduction, which is called the PCA or principal component analysis. Today we will continue with that topic. We will solve some problems and some questions on another sort of dimensionality reduction technique, which is called the MDA or multiple discriminant analysis. We will solve some problems on that today. So let us start with the first problem. So the first problem reads like this: which of the following is or are true for MDA? First option is maximize the intra-class scatter, then maintains the separability of two classes, and third is projection direction may not be the best in terms of minimum squared error. So as you know, in case of MDA, when we try to find the projection direction, we try to find such a direction along which if we project the data, then the projected data will have maximum separation between the classes, or the inter-class scatter will be much higher. So, or in case of two class problem, the between class scatter will be much higher. So, the separability is much more, whereas the intra-class variation is minimized. We try to find such a direction along which the projected data has more inter-class difference but very less intra-class difference. So that is the direction of MDA. So going by that logic, the first option is maximize the intra-class scatter. No, MDA doesn't maximize the intra-class scatter, because if you maximize the within class scatter, then there is more chance of overlapping between the two classes and there is a more variability between the classes. So we do not want that. We want the classes to be concentrated at some locations and the inter-class variations should be more. So we do not try to maximize intra-class scatter, rather we try to minimize the intra-class scatter. We try to concentrate a class at some point. Then so the first option is not true for MDA. So MDA doesn't try to maximize the intra-class scatter. Then maintains the separability of two classes. Yes, it maintains the separability of two classes. It tries to enhance the separability of the two classes by trying to maximize the between class scatter. So this is something that MDA does. And the third option is projection direction may not be the best in terms of minimum squared error. That is also true in case of MDA, because while projecting or while finding the projection direction, we do not take into account the minimum squared error. We try to find the direction by maximizing the between class scatter and minimizing the intra class scatter. We do not put any attention on the minimum squared error. So whatever projection direction that we find, that may not be the best in terms of the minimum squared error. So these projections may not be the best representations of this data in the projected space. So this is indeed true. But as you will remember, last week we did PCA. PCA is the method which is best in terms of minimum squared error, because there our goal is to find the best representation or most matching representation, and that we do by minimizing this minimum squared error. So that is the best representation that we can get. That is for PCA. But MDA do not put any criteria about the minimum squared error. So as we see, the first option is not correct, but the latter two options, option 2 and 3, are correct for MDA. So the correct answer here is C, only 2 and 3. This is for MDA. Okay. Now Moving forward, next question asks, which of the following option is true? A classifier built with MDA results in better class prediction as compared to PCA. So, as you will already understand from all the previous discussions that this is indeed true, because when you apply PCA to obtain the projections of different data points, then you just try to find the best representation in terms of the minimum squared error in the projected space. But you do not put any constraint, or you do not at all focus on the class separability, whether that is maintained after projection or not. That is not taken into account in case of PCA. But when you go for MDA, you are finding the direction by trying to maximize the class separability and minimize the intra-class difference. So, the class separability or the class information is much more involved in the MDA analysis. So, you are intentionally trying to put the two classes far apart in case of MDA, whereas in PCA you do not have any such requirement. So, when you go for classification, then the classifier which is built with MDA, that will indeed be able to better separate the classes or do better class prediction as compared to PCA, because PCA is not a supervised thing, it does not have that knowledge of the class, but MDA is devised in such a way so that it can maintain the separability or enhance the separability. So, when you use the classifier built with MDA, that can give you better class prediction than the PCA one. So, option A is correct. Now, the next option is MDA explicitly attempts to model the difference between the classes of data. As I already said, this is indeed true. MDA explicitly tries to maximize the difference between the classes. This is the objective function that is used to that is maximized to determine MDA, that tries to maximize the difference between the classes. So, this option is also true. Oh, then the third option, there is both A and B. So, that will be the correct option for this question. So, both option A and option B are correct. So, when you build a classifier with MDA, that is better for classification purpose than a classifier with PCA, and the MDA by itself tries to model the difference between the classes. Okay. So, if that is clear, we move on to the next question. Next question is for a two class problem. So, we are considering a two class problem. If SW is within class scatter, mu1, mu2 are the corresponding means, then which of the following is correct for direction of projection using MDA? So, if you use MDA, what will be the projection direction? So, before I explain the answer, would anyone like to attempt? What will be the correct answer for this? Shima is saying the option A. Yes, Shima, you are correct. The option is A. So let's revisit this derivation to see how this expression actually comes. Let us have a look at that derivation here. So, we need to determine the projection direction using MDA. For that, let us say we have a data set with n samples. N samples, and each sample is a d-dimensional sample. N d-dimensional samples are there. Let us say x1, x2, like that you have the samples. Now, let us say you have two classes actually. So, n1 samples among these entire n number of sample belongs to one class and n2 samples belong to the other class. So let's say the two classes are omega 1 and omega 2. So let's say n1 samples belong to class omega 1 and n2 samples belong to class omega 2. So you have n1 plus n2 equals to n. Total you have n number of samples. Among them n1 is from class 1 or omega 1, n2 is from class omega 2. All are d-dimensional samples. Okay. Now according to MDA, you need to maximize the interclass scatter and minimize the intraclass scatter. So first let us try to compute what is interclass scatter. So in case of MDA, interclass scatter is basically, what does interclass scatter mean? It means the difference between, it will capture the difference between different classes. So in case of MDA, we capture this interclass scatter by a matrix or let's say we capture this interclass scatter by the difference of the means of the two classes. Okay. So basically, if let's say mu1 hat and mu2 hat are the means of the two classes in the projected space. Okay, so let me clarify it even more. So initially you have the d-dimensional samples x1, x2 like that, n number of samples. Among them n1 is in one class, n2 is in one class. Now let's say W is the projection direction along which you are projecting your data by MDA. So your projected data points will be something like W transpose Xi. Let us say we denote these by Yi. Okay. So these Yi are your projected data. Now let's say we denote the mean of these Yi's by the mu I tilde. So mu1 tilde is the mean of Yi's for the class omega 1 and mu2 tilde is the mean of Yi's for class omega 2. So if you write mu1 tilde, that is basically summation of, let's say first write it in terms of Yi, summation of Yi where Yi element of omega 1, and since there are n1 number of samples in class omega 1, so it will be 1 by n1. So this is mu1 tilde or mean of the projected data for the class omega 1. Now Yi is basically W transpose Xi. So if you put that, it becomes this. Now this W is independent of the Yi's or independent of I, or to put it better, let's say denote this as I. Yeah. So since the W transpose do not depend on the summation variable, we can take that out. Even we can take that completely out and put the remaining together, 1 by n1 summation over I Xi, I element of omega 1. So you can see within bracket what we have is basically the mean of the Xi's belonging to class omega 1. So let's say we denote that by mu1 without the tilde. So with tilde it is in the projected space, without tilde it is in the original d-dimensional space. So it will become W transpose mu1. Okay. W transpose mu1, where mu1 is the mean of the d-dimensional data points belonging to class omega 1. Similarly, you can compute the same for class omega 2. So, if you denote the mean of the projected data points for class omega 2 by mu 2 tilde, then you can write the expression for mu 2 tilde as W transpose mu 2, where mu 2 is the mean of the data points, original d-dimensional data points which belong to class omega 2. That is, if you want to write the expression of mu 2, that is 1 by m2 n2, since there are n2 number of data points in class omega 2, summation over I element of omega 2 xi. Okay, so this is basically mu 2. This is the mean of the xi points or d-dimensional samples for which belong to class omega 2. So, mu 2 tilde is the mean of the corresponding projected data. So, it can be written as W transpose mu 2. Now, originally we were trying to capture the between class scatter. Right? So, between class scatter, we said that we will capture that in terms of the difference in the means of the two classes in the projected space. So, basically we take the difference of these two as the measure of the between class scatter, rather we take the square of this. Okay. We take the modulus square of this as the measure of between class difference. Between class separation is modeled by this. So, if you expand this expression, you can write it as like that: mu 1 tilde minus mu 2 tilde into mu 1 tilde minus mu 2 tilde transpose. So, this is the expression for the between class separation. Now, you can further put expression of mu 1 tilde and mu 2 tilde as we have found here. Okay. So, if you put that, this becomes W transpose mu 1 minus W transpose mu 2 into W transpose mu 1 minus W transpose mu 2 whole transpose. So, you can simply take W transpose out, W transpose into mu 1 minus mu 2. Again, this will become mu 1 minus mu 2 transpose W. Now, we tell this term mu 1 minus mu 2 into mu 1 minus mu 2 transpose as the between class scatter matrix. This is denoted by SB, between class scatter. So, our expression becomes W transpose SBW. So, we try to maximize W transpose SBW. Okay. This is the measure of the between class scatter. But this how much separation is enough? So, we do not need to separate them infinitely. Some extent of separation is enough. How much separation is enough, that we determine in terms of the intra-class scatter. So, we try to minimize the intra-class scatter and try to maximize the between class scatter. Now, for that we need the intra-class scatter. So, let us say S1 square is the scatter intra-class scatter for the class omega 1 of the projected data. Okay. So, the expression for this will be this is the intra-class scatter for the class omega 1 in the projected data space. So, this is basically the data points belonging to the class omega 1 projected in along the direction w. So, yi's minus the mean of the class omega 1 and into yi minus mu 1 tilde transpose. So, this is basically the measure of the intra-class scatter for class omega 1. So, as you already know, yi is basically w transpose xi. That is how you take the orthogonal projection along some direction. And mu 1 tilde we just saw, it is w transpose mu 1. So, we can put these expressions into this equation to get a even simpler form. So, if we do that, this looks like this. Now, in this expression, the w is independent of I. So, we can easily take the w out of the summation. So, that will make it w transpose summation I element of omega 1 xi minus mu 1 into xi minus mu 1 transpose into w. So, you have w transpose w on both sides, in between you have this term. This is nothing but the scatter of the original d-dimensional data points xi belonging to the class omega 1. So, we can denote this by capital S1, which is the intra-class scatter of class omega 1 in the original d-dimensional space. So, the intra-class scatter for class omega 1 in the projected space becomes w transpose S1w. Okay. Similarly, you have to compute for the other class, since here we are considering two classes for simplicity. So, for the other class omega 2, the intra-class scatter for the projected data will similarly can be derived. So, the expression will be yi minus mu 2 transpose into yi minus mu 2 tilde into yi minus mu 2 tilde transpose I element of omega 2. And if you evaluate this similarly, you will finally get w transpose S2w, where S2 is the intra-class scatter for class omega 2 in the original d-dimensional space. So, if you try to take the total intra-class scatter, that is given by SW, that is equal to S1 square plus, let's say you want to take the total intra-class scatter in the projected space. So, that will be S1 square plus S2 square, and that is equal to w transpose S1w plus w transpose S2w. And if you take w transpose and w common, this becomes w transpose S1 plus S2w. This S1 plus S2 we denote it as SW. So, this becomes w transpose SWW. Here SW is the total intra-class scatter in the original d-dimensional space. So, this projected scatter, intra-class scatter S1 square minus S2 square, that we want to minimize. This scatter we want to minimize, whereas this inter-class scatter, this we want to maximize. So, we can formulate this in a optimization problem. So, the objective function of the optimization will be J, which is a function of W, that is W transpose SBW by W transpose SWW, and you have to maximize this. So, this is our optimization problem. Now, as any other maximization problem, to do this maximization, you can take the derivative of this expression with respect to w and you can equate that to 0. You will get some equation and that will be describing the direction along which you should project in order to maximize Jw. So, let us take the derivative. So, if I derivative del j del w, I will get this. This is the derivative with respect to w. So, to maximize the original quantity, we need to equate this to 0. Then if we simplify, we will get 2 SBW equals to this. Okay. Now, here think carefully, this quantity, this is basically a scalar constant. How, if you want to see? So, this SB and SW are between class and intra-class scatter matrices. So, what is the dimension of these matrices? So, original data is in the D dimensional space. So, the dimension of these matrices will be D cross D. SB and SW will have the dimension D cross D. Okay. And your W, since your feature samples were D dimensional samples you had, so your W will also be D dimensional, or its dimension will be more precisely D cross 1. So, you have cross D cross 1 and in the front you have W transpose, so 1 cross D. So, finally, your expression, finally it all cancels out and it becomes a scalar quantity, right. So, if you just take this much first and do say SBW or SWW, that dimension will be D transpose D cross 1, that will be D cross 1. Now, if you first put 1 cross D, that is W transpose in front, then D cross 1, your final will be 1 cross 1, which is basically a scalar quantity. So, I will erase this part. So, this term that I circled, this is basically a scalar quantity. We can express that as k, okay, or we can express that as lambda, which is the conventional notation. And the 2 both sides always cancels out. So, finally, the expression becomes SBW equal to lambda times SWW. So, as you already saw, this SBW and SWW are D cross 1 vectors and SBW is lambda times SWW. So, the direction of both the vectors SBW and SWW are the same, only they are scaled version of one another. Okay. So, the direction of both of them are the same, but they are simply scaled version of one another. So, thus you got the generalized eigenvalue equation, and this is the equation that determines the W, which is the projection direction along MDA, projection direction according to MDA. Or you can even simplify it. Let's say your SW is invertible. In that particular case, SW invertible. So, SW inverse exists. In that case, you can make w equals to you can make, I am ignoring this constant because this is just the magnitude along the direction. We are concerned with the direction only. So, I am just considering the direction and not the constant quantity. So, in that case W will become SW inverse SBW. This is because we are assuming that SW inverse exists. Okay. Just a minute. Yeah. Now, this SBW, what is this SBW? Let's just go back. So, here as you can see, this is basically your SBW. This is basically the quantity, or let me mark it in some other color. This is basically your SBW, right? So, in this mu1 minus mu2 transpose W, that will again result into a scalar quantity, because the first one is d cross mu1 minus mu2 is d cross 1. So, its transpose is 1 cross d and W is d cross 1. So, finally, you are getting 1 cross 1. Okay. So, this is again a scalar quantity. So, the direction will be along the direction of mu1 minus mu2. The direction of SBW will be along the direction of mu1 minus mu2. So, if you put that here in place of SBW, you will get SW inverse mu1 minus mu2. Here we are not considering the scaling factors, because that is just the scaling factor and it is not changing the direction, and we are concerned about the direction. That is why we are not explicitly taking that into account. I am sorry. So, this is the final direction of projection according to MD. Okay. Now, let us take some examples, numerical examples to find these things. So, the first problem is for a 2-class problem where 4 samples are given for class omega 1 and 4 samples are given for class omega 2. You have to compute the total within class scatter SW. Okay. So, as we already saw, what is the expression of total within class scatter? That will be within class scatter of class omega 1 plus within class scatter of class omega 2. And what is each of this within class scatter? That will be summation, say j element of omega I xi minus mu j transpose, right. So, we need to know the mu j for both classes. So, as you can see, if we take the first class omega 1, then mu 1 is given as 1/4 of 12/4, that is basically 3/1. So, mu 1 is 3/1, right. Similarly, if you compute mu 2, that is 1/4 12/16. So, that is basically 3/4. So, these are the two means 3/1 and 3/4. Now, this is the expression xi minus mu j transpose. So, you have to subtract the mean of the class from each sample of the class and form these outer products and sum it up. So, for the first class we will take, so the vectors that we have are these are the 4 vectors of class omega 1. This is, we are talking about class omega 1. You have to subtract the mean from each sample, and the mean is 3 1. So, you will have to subtract 3 1 from each. So, you will have to subtract 3 1 from this. So, what you get is basically minus 2 0 here, 0 minus 1 here, 0 1 here, 2 0 here. Okay. Yeah. Now you will have to form the outer products of each of these vectors with its transpose. So, minus 2 0 you will take the product with the transpose minus 2 0, and you will get 4 0 0 0. For the next sample, you take 0 minus 1, 0 minus 1 transpose, you get 0 0 0 1. Next is 0 1 0 1 transpose, again you get 0 0 0 1. Last is 2 0 2 0 transpose, you get 4 0 0 0. These are the 4 outer products. Now, according to this formula, you just need to take the sum of these outer products over all samples belonging to the particular class. So, you just need to sum all this up. So, you will get S1 as 8002. 8002 is the intra-class scatter for class omega 1. Similarly, we will do for class omega 2. Here the samples are these are the 4 samples for class omega 2, and here the mean mu 2 is 3 4. So, you will have to subtract 3 4 from each of these vectors. So, minus 3 4 same all these cases. So, what you will get for the first sample is minus 2 0, then for the next sample 3 3 you will get 0 minus 1, then for the next sample 3 5 you will get 0 1, then for the last sample 5 4 you will get 2 0. Minus 2 0, 0 minus 1, 0 1 2 0. Again you will have to proceed by the same way. So, if you see here, we have got the same vectors after subtracting the mean. So, minus 2 0 0 minus 1 0 1 2 0, previously also we had that. So, we will finally end up with the same scatter matrix here also. So, S2 also we will get as 8002. You can proceed in the same way and compute this. You will get S2 also as 8002. Now, we need the final within class, total within class scatter, which is S1 plus S2. So, that will be 8002 plus 8002, both are same here, and we will get 16004. We will get 16004. So, 16004, option B is the correct answer. This is the total within class scatter SW. Okay. I hope this is clear to everyone. So, I am moving on to the next problem. Now, we are considering the same class, same number of data samples, same examples, but previously we computed the total within class scatter. Now, we will compute the between class scatter. So, as you already saw, the expression for between class scatter will be SB equal to mu 1 minus mu 2 into mu 1 minus mu 2 transpose. So we have already seen this here. Here we defined SB is mu1 minus mu2. There is some lag in the slide GNG. Sorry for that lag. Yeah, now it's there. So here you can see SB we defined as SB is mu1 minus mu2 into mu1 minus mu2 transpose. We are simply using that expression here. And in the previous problem we have already computed mu1 and mu2. Mu1 is 3,1, mu2 is 3,4. So we just simply take the difference and take the outer product. So the difference between the two means will be 0 minus 3. So you are subtracting 3,1 minus 3,4. So you will get 0 minus 3. So this difference is basically 0 minus 3. And you have the transpose of that. So 0 minus 3. If you complete the outer product, you get 0, 0, 0, 9. This is your final between class scatter matrix 0, 0, 0, 9. So option A is the correct option for this. Okay. So we have computed total within class scatter. We have also computed the between class scatter for these two sets of data points. Now, as the next problem, we will try to compute the direction of projection W using Fisher's linear discriminant for this same set of data points. Okay. We are trying to compute the direction now. So what is the expression for the direction? That is SW inverse mu1 minus mu2. Right? Mu1 minus mu2 we just computed 0 minus 3. Mu1 minus mu2, this quantity is basically 0 minus 3. And we have SW inverse. So we will have to compute SW inverse. So as you know, the formula for inverse will be 1 by determinant of SW into adjoint of SW. Right? That will be the formula for inverse. 1 by determinant into adjoint, where adjoint is basically the cofactor matrix transpose. So here SW determinant. So we computed SW here. The determinant here will be, determinant of SW will be 64 minus 0, that is 64. Determinant is 64. So 1 by 64. The adjoint of SW, which is cofactor transpose. So if you take adjoint of SW, so you have cofactor of 16 is 4, there is 0, 0, 16, this transpose. Okay. So if you put that, it will be 4, 0, 0, 16. So you have 1 by 16, 0, 0, 4. So basically it is a diagonal matrix. So you can simply take the inverse of the diagonal elements, that will give you the inverse of the matrix. So here also we got that. So the diagonal matrix was this. This one was our diagonal matrix 16, 0, 0, 4, and the inverse that we got here is 1 by 16. Oh sorry, this will be 1 by 4. One by 16, 0, 0, 1 by 4. Now you have to take the product. So your final direction will be 1 by 16, 0, 0, 1 by 4 into 0 minus 3. This will become 0 minus 3 by 4. So here also option A is the correct answer. 0 minus 3 by 4 is the direction found according to Fisher's linear discriminator. This is the direction according to Fisher's linear discriminator. Now in the next problem it is asked that we are still considering the same set of data points and the two classes omega 1 and omega 2, you have to find the projection of the point 14 on W using the Fisher linear discriminator. So, the W that we got in the previous problem is 0 minus 3 by 4. 0 minus 3 by 4 is W, and you have to take the projection of the point 14 on this W. So, the formula for orthogonal projection is W transpose X. Okay. So, if we want to put the values, we will get 0 minus 3 by 4 transpose, and X is here 14. So, if you multiply, you get minus 3. Option D is the correct answer. So, the point 14 in the original space is projected to the point minus 3 on W, or in the projected space it is the point minus 3, okay, according to Fisher's linear discriminator. So, this way you can compute the projection of all the points along in the projected space. So, if you do that, then you will get one dimensional representations of all the data points, and those projections will be the ones such that the intra-class scatter among them is the minimum, whereas the inter-class scatter among them is the maximum. Okay. And this 14 is projected to minus 3. Okay. I hope this is clear to everyone. If you have any question, you can raise it at any point. Okay. Now, let us move on to the last problem of today's session. So, for this 2 class problem, we have already found out the projection direction. Okay. So, now this question is asking that find the separation or the absolute value of the means or Euclidean distance before and after projection using Fisher linear discriminator. So, you will have to find the separation of means. So, you have the means of both the classes, you will have to find the separation between them, and separation is in terms of the absolute Euclidean distance, and you will have to find this separation of means before and after projection. Okay. So, before projection, what were your means? mu1 and mu2. Those were, let us go back and see what they were, 3 1 and 3 4. Okay. Those are the 2 means. So, what is the Euclidean distance? Let us say I put that as d1. What is the Euclidean distance between them? That will be, so the distance vector between them is given by 0 minus 3. So, the separation or Euclidean separation is equal to root over 0 plus minus 3 square this is equal to 3. This is before projection. The separation of the means, the Euclidean distance is 3. Now, after projection, here I will do after also. After projection, your means are mu1 tilde and mu2 tilde. And what are those? So, as we already know, mu1 tilde is W transpose mu1, mu2 tilde is W transpose mu2. We have already derived this. So, just simply compute this. W is in our case 0 minus 3 by 4, 0 minus 3 by 4 and this transpose, then we have mu 1 which is 3 1. Okay. So we have mu 1 tilde as minus 3 by 4. Mu 1 tilde is minus 3 by 4. And similarly you have mu 2 tilde which is W transpose mu 2, that is equal to 0 minus 3 by 4 transpose, mu 2 is 3 4. So your final value will be minus 3. Okay. So here if you try to compute the separation, that is equals to minus 3 by 4 minus minus 3 which is plus 3, that is equals to 2.25. So the separation before and after projection are 3 and 2.25. So option D is the correct answer for this question. Okay. Okay. So these were the problems for today's class. So I hope I could explain the problems and the concepts. If you have any questions at this point, you can raise the questions. I'll pause here for today. If you have any question, you can put it in the chat or you can directly unmute yourself and speak up. Okay, so it seems there is no questions. So that's it for today, guys. We will meet again in the next week with the next set of problems. Thank you everyone for joining. Bye bye.